Well, continuing with our program, at this time, we're happy to welcome to the stage our next presenter. I hope. I would like to introduce Marco Pesci, presenting a software-defined metro fabric architecture using disaggregated switching and VXLAN. Marco is a global technical architect at Pluribus Networks and traveled from the San Francisco Bay Area to join us today. This is Marco's first time presenting at NANOG, and it's a pleasure to have him speaking today. Welcome, Marco.
Thank you, Steve. Thank you. Very excited to be here, back on stage after quite a few years. And I wanted just to thank you, my mentor, Melchior, Valerie, and the NANOG staff for having me. Let me just grab this. I'm going to need it. So the title is quite long. I tried to bid for the longest title prize at the conference, but I think I failed, and I'm pretty sure the acronym at the end was probably the point where I failed. Anyway, that's fine. So what I want to discuss today is a technology that actually is native to the data center environment that uses VXLAN and top-of-rack switches with SDN, with an SDN controller, and how that can apply to metropolitan transport. And like many other stories, this starts back in 2016. In 2016, I met a mate in Madrid. He started working for this major company that was offering data center space to big customers, big enterprise customers, but also telco operators in the major cities in Spain and Portugal. And he tells me, well, Marco, I have this new project. He's a network architect, very, very brilliant. I have this new project. There are several customers who started asking me, can you guys sell us point-to-point services between cities to interconnect our data centers? And so I've been evaluating possible solutions, and the one that I have, which is MPLS based, is too expensive. So the project is gonna be canned. So is there something you can do, since you're working on VXLAN, to provide a similar service? And I told you, well, actually, yeah, we have just developed a VXLAN pseudo wire, and it's the first in the industry. I mean, 2016, there was no concept of VXLAN pseudo wire yet in the preliminary EVPN drafts. So that's how it started. And eventually we did a POC. It went very well, and customers started buying the solution. They liked it very much. And so now we have Real Madrid. We have customers like Vodafone passing MPLS traffic between cities. So that's how it started. 5 years later, I'm here to kind of show you the experience that I had for this type of project. A little bit about myself. I have the fortune to work for a company, Pluribus Networks, that provides an awesome technology for data center solution, which is about using a software network operating system that runs on commodity switches and has an SDN abstraction inside the OS itself without using an external controller. And I'm also lucky for the fact that the company is quite small, so I can have a dual role. So I'm actually leading the technical field worldwide, but I'm also contributing a lot to the product definition and working with our engineering team to develop the product and how it evolves. As a background, right now, I've been focusing a lot on a new technology called DPU, data processing units. You can think about it like a switch in miniature that has a network interface card form factor and sits inside your server, but has hardware accelerated network functions. And I've been doing a lot of VXLAN-based solutions for distributed data centers, active-active DR solutions. As an experience, I've been with Pluribus 7 years, previously almost 20 years with Cisco and others, a lot of routing and switching. I always liked and had a little bit of a passion about being hands-on and how to then manage the solution. And so if it was, let's say, to have an experience with, for example, TL1, which is the CLI very structured, but also, concept like stacking and virtual switching or satellite switches. That's really what drove my experience in networking in the past 25 years. So today for the discussion, right? So I like to kind of evaluate the different and predominant architecture that are used today or that have been evaluating today for Metro Ethernet transport. I like to focus particularly on L2 VPN services and also in terms of layers, definitely metro aggregation. But this principle in theory apply also to L3 VPN services and other layers in the network. I like to take a look and show you how the modernization of data center technologies can also have applicability into distributed networks like Metro Ethernet use cases. And particularly, I like to contrast a little bit how the different technologies differ in terms of scale, both on the operational scale and also control plane and performance in general. And finally, before wrapping up and taking your questions, I'll be happy to show you a real-world example. Okay, so for L2 VPN, MEF compliant, MEF stands for Metro Ethernet Forum, services, the de facto standard, the predominant technology today is VPLS. But the recurring questions that most of you have and a lot of my customers had is there a better way, is there a better cost-effective technology that takes me out for being obliged to use very expensive hardware? And is there a better way, we just saw a presentation earlier, to manage a distributed set of nodes that kind of takes down my operational cost for the solution? So one of the answers that the industry has to offer and has been offering for decades is Q&Q, layer 2 fabrics, not just saying Q&Q, but others as well. And the nice thing of this bridge fabric is the fact that historically there being the first attempt to use commoditized switching to provide high gigabit performance to distributed networks. And in Metro Ethernet, okay, Q&Q, but also, for example, I have some competitive information for the Asian market, South American market. Huawei has been using triple Q in the transport network. Most of you had hopefully a good experience with Brocade VDX, which was a trill-based fabric. So all these experiences, different technologies, had in common the simplicity of the solution. A VLAN or a VLAN-based service as a concept in a bridge network is conceptually simple, structurally simple, and also from a management perspective is kind of a plug-in network where I define the service. I don't think the pointer worked, but in this diagram where I'm visioning a Metro Ethernet network with 3 main sites where I have a customer blue at these 3 main sites asking for a mesh VLAN service. So this type of offer can be, at a very reasonable operative cost, can be deployed by just defining the VLAN in one of the sites. And then in the moment I assign this VLAN to each of the 3 ports in the 3 different sites, well, because this is a bridge network, the VLAN gets just distributed. So from a management perspective, the effort is, quite negligible. And so this is really what I like of this type of architecture. Unfortunately, you know, a loop, a layer 2 meltdown is the worst nightmare for a network administrator. And there's some fragility in the architecture here. There's also some issues in managing multipathing efficiently. For example, what I'm representing here in this picture, there are some dotted lines that represent hot standby links that are not in use. So these are kind of the challenges that prevent layer 2 fabrics to kind of grow in size. And there's also some limits definitely in the scale being a VLAN technology. But still a good successful alternative to other technology, like, for example, IP/MPLS. And definitely IP/MPLS is the predominant, and one of the great things here is you know, bringing a resilient transport with a layer 3 routed network in the transport. And so implementing you know, best path efficient routing, including active-active ECMP-based routing. So definitely that's the advantage. On the, let's say, minus side, we know that this type of protocols are quite demanding. There's definitely an operational cost in deploying this type of network, but there's also a hardware cost associated with the fact that I need a router or a highly performant switch ASIC, like, for example, Broadcom, Qumran, or Jericho families. So is there an alternative to this? And yes, VXLAN and EVPN. This is not new. What brings a VXLAN fabric to the picture here? The nice thing of a layer 3 transport. So VXLAN is a UDP-based protocol. It's very nice to firewalls, but beyond that, the main interesting part is that it is a light encapsulation protocol, and it's nicely load balanced. So I can have flow balancing, very efficient per flow based on the VXLAN UDP entropy. And definitely, you know, I can leverage all the pluses of having a routed transport in the core. The good thing also is when I add a control plane to the VXLAN transport that is EVPN, I can really, you know, refer to a model where there's a good separation between an underlay network, which is basically the core transport, and the overlay network, which is where we deploy and we offer the services to the customers. And that, you know, kind of gives us different tools to attack each of these two components of the solution with the best architecture. So, for example, for the underlay, which is the part of the network that I deploy first, is my day one deployment. I can, you know, depending on the topology, decide where I put my PE VPN speakers, right? For this simple topology, for example, I can have 3 speakers where in the sites where I deploy the service, and I can have 3 mutual EVPN adjacencies. So that means that the 4 routers in the middle just run an IGP or a BGP protocol. So as simple as that. Of course, if this topology grows in size, then I can still use EVPN to peer up with the upstream switches, and so kind of limit the number of adjacencies. So I have many options, like for any routed design. So that's really great. And once the underlay has been designed and deployed, then I can focus for my daily operation just on the overlay services. And I define them at the edge in every site. And then magically, thanks to the EVPN control plane, VXLAN tunnel are created site to site for each service, like, for example, the blue service here towards the customer sees. This is not new, right? There's a lot of literature. For example, Richard Steenberger have presented a paper at NANOG in 2018. But also I found a reference in Brazil IX from a PLM works for Extreme. And the conclusion is VXLAN is a great tunneling technology. It's very light compared to MPLS encapsulation. It requires some control plane, though. One alternative could be an SDN centralized controller approach, but the problem with that, it doesn't scale. And so EVPN is a preferred control plane approach because it scales in terms of network size and multi-tenant size scale. Now, why we haven't seen so many deployments, or at least in my experience, I don't see a lot of EVPN deployments in Metro. I think one of the reasons is the complexity of the EVPN configuration. So I talk to many customers who tell me, well, actually, yeah, it's nice, but at the end, for the L2 VPN, I need mostly our point-to-point. Well, I just use static VXLAN tunnels. I don't use EVPN at all. Others have been looking at management solutions that work out of the box in a server. There's, of course, a lot of home-built automation that is necessary to orchestrate such a complex configuration where I have, for example, for L3 VPN service, I need about 30 lines of code per switch, which is a little bit too much. If we look at this problem a little bit more closely, the problem I need to solve is the fact that I have to deploy a service in 3 sites using EVPN, and the configuration in these 3 switches, or 6 switches if there's redundancy, needs to match. And this is not an easy task. First, because there's high code that needs to be kind of abstracted somehow. But the main problem is the configuration state of each of these switches is completely independent. They are on their own. Even if I'm using an orchestration system that manages each of these switches using SSH sessions, it's not that a switch is aware that he has to speak only to the management system, to the automation, Ansible tower, etc. Right? So if I'm a network admin and I'm using the credential that the automation system is using, I can go on and switch and try out something, maybe a little bit of a sandbox, right? And then what happens when, for some reason, the same identifiers are used for a service in production to a customer, right? So either my automation system fails, doesn't know how to roll back, it's very difficult to troubleshoot the problem, or maybe I can, just have a silent go, well, the service was already there, let's go ahead, no alarms, no warnings, and then what I end up is, well, that customer service is no more isolated. So definitely these are the things that, make us scratch our heads. How can we solve this? If you allow me to take a further look at the configuration, the problem also derives from, 30 plus years of history inside switching and routing code. And all vendors are kind of in the same situation here, right? So we developed different interfaces, different modules that just got reused when we implemented VXLAN and when we implemented EVPN on top. So for example, if you kind of go through an EVPN config, you may recognize 3 main blocks of configuration. These are completely independent structures, okay? There's the definition of the service locally, right? The VLAN, so that I can attribute these services to physical ports facing the CE side. I need also to identify the service in the data plane, but towards the transport side. So I need for example, to define a VXLAN VNI identifier in the VXLAN realm. And then there's the EVPN control plane where I need to define a route distinguisher. I need to import and export route targets. Now, some of the vendors have improved, offer some compression of this configuration, but the problem still exists in the majority. So I need to make these three components match inside one switch, and I need this configuration state to match across my entire network. So if I have a mesh service with 10 nodes, then I may end up in consuming almost, hundreds and hundreds of lines. And how can I scale to thousands of these services? So that's the problem that we have tried to resolve. Let's put some sort of software-defined abstraction, and let's try to run it inside the switch itself. Let's try to rewrite the code so that we can define an object atomically for an entire distributed network. So the approach is not that different from EVPN and VXLAN principle. We still have a distinction between underlay and overlay. The underlay is a routed network. You can use any routed technology. You can use eBGP. You can use an IGP. And you're completely free to pick up the design that you want. But then we have some interesting application that runs on the switches at the edge of this topology that creates an SDN cluster or an SDN domain. So essentially, it's like a federation. It's a mesh application that it's based on mutual peering across all these switches that participate in the S domain, and it's based on secure TCP. It's a TLS-based application. Okay, so that creates a logical cluster that basically turns every switch into a line card of a virtual chassis. And one of the benefits that this architecture provides is a single point of management, a single point of truth. So that means that when I have to define my service for customer blue, my three-way service, I define it once. I define it once by connecting to any of the switches in the topology, using SSH or using a GUI, right? But the switch and the SDN mesh takes care of bringing that configuration and committing it to all the switches. If something goes wrong on one of the switches, like in the example I made before, well, that configuration command will fade. So I go back and I check what's wrong, but I'm never in a situation where I have an inconsistent provisioning state. So kind of to summarize what we saw BGP VPN, which is a proven technology that scales very well, but has some caveats in terms of management scale. An SDN centralized controller approach has been confirmed by the industry like not being a good fit because it lacks the network scalability that we need to have for a distributed network solution like this one. So a distributed SDN approach that works either in conjunction with EVPN for the forwarding plane or without EVPN, with just routing is, in my opinion, this is my thesis, the great approach for this type of networks. At least it provides a way to have a valid, low-cost alternative to VPLS. I wanted to spend just 2 minutes on, because probably distributed controller versus centralized controller is a debate that is a little bit new to this audience. So let me just spend 2 minutes here and comparing the two. So on the left, I have the centralized approach. On the right, a distributed controller approach. The goal is the same. So I have a network here with 6 leaves and 2 spines, and I want to manage it consistently as a single point of touch. When I use a centralized controller approach, the domain of the network includes also the spine, includes also the transport. And when I use a distributed controller approach, the spine are just transport node. It could be running any routing stack of any vendor, right? And this is kind of one of the advantages that the distributed controller approach brings in. Then, of course, in the distributed controller case, the controller resides inside the switch, and the control plane scales as the network grows. In the centralized controller situation, I have a single controller. I need to make sure I have high availability, some clustering technology there that also allows the controller to be present at any site, potentially, because I may lose one site and I still need the controller. So definitely, these are cost implications, and architecturally, although it may look simple, the centralized controller is not a good fit for a distributed network. So that's kind of the conclusion. And one last thought. Data center switching has been kind of evolving, right, from chassis-based solution to scale-out solution. The solutions that are available today with commoditized top-of-rack scale very well in terms of number of tenants. And so I don't see why this transformation can also apply to distributed networks. So I don't see the need of using deep buffers or custom silicon because everything we need is actually there. It's just a matter of applying the best design practices that we experienced in data centers also to distributed networks. And at the end of my presentation, I show you just a quick example here of a real-world network. I'm considering here a kind of a hybrid service provider that maybe started offering edge data center services and specialized into some specific application. For example, the customer I have in mind here started working with the film, with the movie industry, and specialized in image processing a lot. And of course, when you start offering certain services, you care about the performance of the service. And the performance of the service depends definitely on the connectivity. And so the higher the bandwidth I'm able to offer the service to, the lower the latency, the more quality the service has, and the better I can monetize the service and compete with public cloud, for example. So that's kind of the story here. The key takeaways are on the ring on the left, right? And I'm using here all top-of-rack switches that provide 10G to 25G down to the customer. On the ring on the left, I can replace a G8032 ring with a routed ring that uses best path for routing. I can go further than that. If I introduce DWDM, I can actually turn a ring into a logical leaf and spine. This has been proven. There's a lot of literature. Look, for example, at AMSIX, the Netherlands Internet Exchange company. They wrote a paper about this, also using Pluribus technology. And the bottom line here is BGP, end-to-end, from top to bottom. And I can use an SDN domain that stretches across all the distribution network, and that allows me to define customer services at one click in one atomic operation. So that's the conclusion of my presentation. So I'll, Steve, if you want to come for any questions.
Again, folks, if you have questions, feel free to use the microphones in the room. Any folks who are remote or would like to solicit questions over the chat interface, I'm happy to relay them here.
En français aussi, hein, comme vous voulez.
This may be a dumb question because it's not.
Yeah, there are no dumb questions.
Oh, I can break that. But when you've got a centralized SDN control plane, the controller touches all the nodes to ensure the configuration is in sync. If you have a node in a distributed control plane like this that becomes isolated,
Yeah.
How does it resume sync with the system when
Right.
you don't have that centralized plane?
Right. Or how do I manage split brain situation, right? So
Right.
when a node goes off, the node has still a configuration that is local. It's just a copy of the entire fabric configuration. So it has a way, even if it becomes isolated, to continue to provide local services. Then from a management perspective, if I lose a node and it's a temporary situation, well, I go and resolve that. If I really lost, for example, a switch because of a major problem and I need to replace that, then I'm kind of in a situation where I cannot create fabric-wide services because there's no consensus, right, from this node that went offline. So one possibility I can do is I basically exclude from participating to the consensus. So that allows me to continue operating the network and deploy new services. And by the time the switch comes back, maybe 2 days later, I found a spare and I replace it. Well, at that point, the switch comes back, joins back the SDN fabric, and well, the switch, it's very different from the VPN, right? The switch has a conscience that is part of an SDN domain, so we'll just ask for the source of truth. So we will ask the other switches in the fabric, hey, what's the latest configuration? It gets it and comes back up, so all normal. So that's how we manage it. It works very, very well. Thanks. Any other question? Steve,
Remote.
you're good?
As good as I can be.
Then we're good. Merci. Thank you.
Thank you, Marco. Thank you for your time. Appreciate it.